Okay, yeah, thank you. I'd like to thank the organizers for organizing this workshop on optical pumped magnetometry and give me the opportunity to talk about diamond magnetometry. So I am Ara Rahimpour. I come from Mainz, to be more specific, Helmholtz Institute, which is located at the Johannes Gutenberg-Universität of Mainz campus. So this study is supervised by Dr. Arne Wickenbrock, and we are a part of the bigger group, matter-antimatter section at the Helmholtz Institute, led by Dr. Dmitry Butker. So first, I'd like to introduce the Diagnose project. Then we will continue the talk explaining nitrogen vacancy centers in diamond. Then quantum neuroanalyzer design and implementations will be discussed, and the current status and the future plans will be presented. Here on the right, you can see an AI-generated image, which kind of looks funny. So in the future slides, we will see how it is relevant to this talk. So Diagnose is short for diamond-based quantum sensing of neurosurgery. For neurosurgery, this is a lighthouse project supported by German government's quantum technology initiative. So 11 partners are involved, partners from industry, university, and university clinics around Germany. So quantum neuroanalyzer, here you can see on the left side, you can see an schematic of the device sensor. So it is basically an imaging endoscope based on diamond with special solid state defects in them. So the initialization and the readout is done optically, and it is going to provide different imaging modalities such as magnetic map, NMR map, and conductivity map. So specifications of this sensor will be picotesla per square root of hertz sensitivity, the bandwidth of kilohertz or more, and also spatial resolutions of tens of micrometer. On the right-hand side, you can see the actual image of the sensor. In the next slides, it will be discussed more in details. So for those who are not familiar with nitrogen vacancy centers in diamond, so as we know, diamonds are beautiful and well-ordered arrays of carbon atoms. But physicists are especially interested in a special type of defects in them when two adjacent carbon atoms are missing, and one of the vacancies is substituted by a nitrogen atom. So here you have a NV center, or a nitrogen vacancy center. So specifically, we are interested in the negatively charged color centers in diamonds due to their spin properties. What happens is that the ground state and excited state each have triplets. So a 532 nanometer green laser will excite the state into the excited state, and after emitting green light, the color center starts to fluoresce in a lower frequency light, which is red light. But this red light's intensity is different according to the spin state. So on the ground state, if it is in the state, it is shinier or brighter than when it is at the MS plus or MS minus state. So on the right-hand side, you can see a graph, so a spectrum of the fluorescence versus the frequency. So when an oscillating magnetic field is applied to the diamond, what happens is that the red lights start to get dimmer, and then it gets gets its initial intensity. So at this 2.87 gigahertz, it will from MS0, the state will go from MS0 to MS plus or -1. This happens when there is no biased magnetic field applied. So if there is a magnetic field around, these resonance will start to split, this peak. And depending on the separation of these peaks, we will realize how much magnetic field actually is sensed by the color center. So diamonds are made like by lab-grown artificially, and two well-known methods are available, chemical vapor deposition and high pressure, high temperature method. So there are several advantages of using the diamonds, nitrogen vacancy centers in diamond. They can be operated at the ambient temperature and pressure. No cryogenic or no high temperature or high pressure are needed. They are in solid state form, so they can be easily placed into the setup or the sensor that one would like to use. And also the concentration, due to their concentration, they can be used for different application that one will be introduced in this talk. Especially, we are interested in the neurosurgical applications. So a sensor that is made based on this nitrogen vacancy center will be used in a neurosurgery environment to improve neuronavigation by providing local magnetic and electric measurements. So, for example, here we have a simulation. If it starts, no? I think, yeah. So this is a realistic image simulation of a neuron. So to see actually how much magnetic field is produced around these neurons by measuring the current and the voltage that is produced along this realistically simulated figure. I'll go back to, yeah, okay. So going back to this funny AI generated image. So here, one of them says the brain fits the endoscope, yay. So obviously we cannot fit the brain to the endoscope. What we can do is to fit the endoscope, or what we are going to use to fit the brain and to see, to meet our requirements. There are technical challenges currently during neurosurgery. So to share a few vision that we motivates our study is that, for example, one of them is the ergonomic and the geometrical situation during the neurosurgery. It is this sensor, we hope that it will be convenient during providing magnetic images and also providing high resolution and real-time detection. So here we have the single pixel sensor that is available right now. Here you can see the design, and here the actual sensor here. So to mention a few of the engineering feature is that thermal management, because the holder that contains all the optics, it is supposed to help us with this thermal situation, because we cannot allow the sensor to get heated. It is going to be used in an intraoperative situation. The sensor is compact, meaning all the optics, the diamonds, everything is contained in a handheld device. The sensor, like the initialization, pumping, readout, and all the optics are one-sided, meaning there is no obstacle between the diamond that is going to measure or see what magnetically event is happening at the tissue under study. So there's no space there. So here you can see the sensor head, and here there's a little dot here on the microwave board. This is actually a diamond similar to this one that was in a study published last year. The same diamond was used. So a 180 micrometer diamond tip here with NV centers will allow us to do the magnetometry. This is glued onto a diamond lens. So yeah, basically it is going to be a sensor along with a portable rack that can be transferred and shipped into other partner institutes for further studies. At the moment, the sensitivity optimization is ongoing. So our target sensitivity is picotesla or below picotesla per square root of hertz. At the moment, we could get 25 picotesla, but I do not have a graph to show that here. But the study is ongoing, especially for the past 3 to 4 weeks. It was a nonstop optimization and experiments going on. Also, an MEG and an MCG and ECG measurements are ongoing at this magnetically shielded room. Here you can see the sensor inserted inside the magnetically shielded room and the rack that contains electronics and also the optical table. So it would be nice to actually see some signatures of MCG and ECG and see the correlation between the two. So it can help us with the future biomagnetic measurements that will be done. So for the future steps, after the calibration and the optimization of the sensitivity, the device will be shipped to our partner institute in Freiburg for biomagnetic measurements. So the imaging setup is ongoing. So I discussed a single pixel sensor, but it is going to be multi-pixel in the future. And also 0 to ultra low field measurement will be done by our, partners that are located at the Helmholtz Institute. They are actually our neighboring lab. So to conclude this talk, Q&A based on nitrogen vacancy diamonds is a viable magnetometry sensor. So picotesla per square root of hertz sensitivity allows us to detect neural activity during neurosurgery, and also special resolution of tens of micrometer and kilohertz bandwidth will make it a convenient and new generation of intraoperative detection device. So here you can see some people that are involved in this study. This study is led by Dr. Ara Rahimpour. 3 PhDs and 1 postdoc are directly working on this project, but it is not limited to these people. We also have other partners in other institutes or our institute in the different labs. So I'd like to thank my colleagues for the nonstop work, especially past couple of weeks. And I'd like to thank you for your patience and listening to the talk. I'd be happy to answer questions if there are any.